the Big Bang was not the beginning. The Big Bang was followed from the remote future. And what happened before was this exponential expansion, because it's just like what we see now in our eon. This theory tells us that there is no beginning and no end, because Einstein originally put it in for two wrong reasons. And he told me, look, you're wrong. And I said, I'm wrong.
作为当代最具影响力的物理学家之一，彭罗斯提醒我们，你所身处的这个宇宙，也许既非第一个，也不会是最后一个。这个观点彻底挑战了我们对唯一宇宙的直觉想象。他主张，我们的宇宙或许只是无数先前宇宙中的一个篇章，像季节轮替般在宏大时间尺度上接力上演。
There can be infinite number of dimensions. And when Einstein heard about it, he did not like it at all. He regarded this as mathematical sophistry. Without that picture, general relativity would be dead. The mathematics has its own existence. We don't create it, we discover it, or we discover parts of it. It would still be there if there had been no human race. It's so elegant, powerful, universal, and beautiful that they think that the physical world must operate. It's very abstract, but nevertheless it is very permanent.
在他看来，大爆炸并非从无到有的起点，更像是一次宇宙舞台的换场与衔接。那是一种更古老历程的延续，牵涉极端时间尺度与热力学规律，远超我们日常直觉所能轻易把握。更令人惊讶的是，他认为前一个宇宙的蛛丝马迹或已隐身在我们头顶的天空，特别是宇宙微波背景的细微纹理之中。
Maybe the Big Bang is an interesting event, but not the beginning of time. This reality might be one of many. String theory does have the capacity to describe the world as we know it. Principle is the idea that we could be visited by aliens a crazy idea? No, it's not crazy. If they're a billion years ahead of us, they're not building spaceships and coming to planet Earth because they don't care about us. Maybe the particles do have some kind of version of consciousness, some kind of proto-consciousness, a little bit of consciousness in the electron, in the quark, in the protons. Where does it come from?
在本片中，我们将循序拆解彭罗斯的革命性构想，从理念、数学框架到观测线索。这套观点或将彻底改写我们对宇宙起源的理解。
So, Stephen, everyone wants to know what was around before the Big Bang.
Nothing was around before the Big Bang. According to Einstein's general theory of relativity, space and time together form a space-time continuum or manifold which is not flat, but curved by the matter and energy in it. I adopt the Euclidean approach to quantum gravity to describe the beginning of the universe. In this, ordinary real time is replaced by imaginary time, which behaves like a fourth direction of space.
Mm-hmm.
In the Euclidean approach, the history of the universe in imaginary time is a four-dimensional curved surface, like the surface of the Earth, but with two more dimensions. Jim Hartle and I proposed the no-boundary condition. The boundary condition of the universe is that it has no boundary.
Okay.
In order terms, the Euclidean space-time is a closed surface without edge, like the surface of the Earth. One can regard imaginary and real time as beginning at the South Pole, which is a smooth point of space-time where the normal laws of physics hold. There is nothing south of the South Pole, so there was nothing around before the Big Bang.
仰望苍穹似乎单纯宁静，但当你用仪器去测量，它立刻展露出层层细节与复杂脉动。天幕无边无际，肉眼可见的繁星其实多是别人的太阳，而在它们周围，常常还围绕着行星与卫星，构成各自的世界。星光之间多为近乎真空的黑暗，可真正支配宇宙演化的，往往是潜伏其间的暗物质与暗能量。
A space-time singularity. Space and time come to a stop.
Yeah, it's about cosmology and about the questions that cosmology raises. So if you're interested in the science of how did the universe begin, even questions of what may have been there. Is the universe eternal? Is there such a thing as before the Big Bang? What is the future of the universe? How does complexity emerge spontaneously in a universe? I mean, we sort of take it for granted that there's a Big Bang and it's all hot and there's just this kind of hot glow of stuff. And out of that, spontaneously, in 13.8 billion years, you get something like the Earth with a civilization and life on it. So how does that... Do we know anything about that? I mean, we do. I'm asking the question rhetorically. So it's really about showing the size and scale of the universe, but addressing those questions that I think everybody has about what does it mean to be human, this tiny little finite life that we lead in a possibly infinite universe. How do you make sense of that?
一谈宇宙尺度，动辄数十亿星系，各自容纳数十亿恒星，距离以光年计算，光走1年的路程，远超我们日常单位的想象。这些数字未必好背，但足以传达一个讯息：宇宙之大，超出人类直觉的极限。它们一方面昭示宇宙的广阔与多样，另一方面也提醒我们个体生命在其面前何其渺小，从而激发谦卑与探索的勇气。
We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed and you know how many galaxies you've counted, and then you can spread that across the wider universe. And you get this picture of a vast and possibly infinite universe. We know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. Can you picture infinity? Well, no one can picture infinity. We say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. So you can run time backwards, if you like, to find out when they were all on top of each other. It's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. When I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. The idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work.
自古以来，人们不断追问万物如何开始，这种渺小与宏大的对照，始终萦绕在人类思想长河之中。这个问题被反复抛出，或以神话叙事，或凭数学推演与观测验证。在远古时代，答案多源自神话与传统及超自然叙事来解释天象。这些故事把可见现象纳入更大的叙事，神奇、英雄与具意志的自然力量共同编织世界。它们以各自文化语汇呈现，既解释季节更替，支撑社会秩序，也在失落时提供安慰与意义。随着社会进步与学术兴起，另一套语言理性与实证逐步登场。希腊与印度哲人试图以自然规律解释世间变化，从原子论到5大元素皆属其努力。数百年后，现代科学以望远镜、光谱学与数学模型取代神话叙事，使观点能被观测与数据检验。近几个世纪，知识重心由讲故事快速转向做测量，节奏愈发加快。哥白尼与伽利略指出地球非万物中心，彻底改变我们看宇宙的视角与尺度。牛顿以万有引力与运动3定律，建立可精准预测天体与抛射物轨迹的框架。20世纪2大理论革命，相对论与量子力学，再度改写物理规则。广义相对论把引力从力的概念转译为时空几何的弯曲效应，时空合而为一，并随质量与能量的分布起伏弯折影响物体运行。虽未直接给出起源答案，却提供可推演与可验证的框架，让问题变得精确。到了20世纪初，科学界普遍接受宇宙有历史会演化的观点。哈勃以红移观测揭示星系彼此远离，证成宇宙总体在膨胀。把时间倒拨，早期宇宙必然更炙热、更稠密，近似一锅宇宙原汤。大爆炸遂成为那段高温高密的通称。更精确地说，是空间本身迅速伸展。对大众而言，这个说法再次唤起古老疑问：最初的那一下究竟从何而来？到底是必然的物理结果， 亦或某种偶然触发引发初始条件。这触及科学与形上学的分界，是造物者设计还是定律自行演算所致？面向可检验答案的科学家，倾向把宏大问题拆解为能量侧与建模的子题。方程解是否允许从高密度状态平滑连接至当前的加速或常规膨胀？粒子互动和合成历程与光子散射会留下哪些可量测的指纹？例如微波背景起伏、氢元素风度、星系大尺度结构，皆是追索远古的证据。
Einstein's equations require what's called a cosmological constant. It's usually called lambda. These days people call it dark energy. And it causes the universe to expand and expand and expand. And this behavior is in all the cosmology books. If you put in this lambda, the cosmological constant, and when it's positive, that's what it does. So that's pretty well a picture of the universe as we now believe it to be, except people usually think right at the beginning there is something called inflation. This inflation was supposed to have taken part in the universe's activities in the first about 10 to the minus 32 seconds. So think of 1 followed by 32 zeros. 1 over that fraction of a second, in fact, is supposed to have been within the time that the inflation took place. You see, this expansion looks very much like what we see now as this exponential expansion of the universe from the observation of distant supernova stars and all sorts of other things which fit together to get the picture that that's probably what the universe is doing now. But this view is that within these first 10 to the minus 32 seconds, it did this other exponential expansion and expanded by some huge amount in that tiny little point. Now, I never liked this, partly because it didn't fit in with Einstein's equations very happily, partly because, well, it didn't do half the things that it was supposed to do. It's supposed to smooth out the universe, and it doesn't do that. However, if we don't have inflation, you've got to have something a bit like it.
在这些追问中，彭罗斯以严谨几何与大胆想象双线并进，影响深远。受训于纯数学的他，将拓扑与微分几何工具引入引力与宇宙学，处理空间、时间与起点的根本议题。上世纪60年代，他发展出一套刻画整体时空结构的定理与技术，成为后续研究基石。更明确地说，在相当宽松的条件下，广义相对论不可避免地导向起点，也就是常规物理在引力坍缩极限处失效。于是起点从猜想变为定理推论的必然产物，地位大幅提升。凭此与相关贡献，他与霍金共享沃尔夫奖。2020年更因黑洞预言之稳健性获颁诺贝尔奖，实至名归。这些荣誉不仅是肯定，更象征他塑造了我们理解引力极端行为的方式。他的科学旅程兼顾技术细节与宏观提问，既严密又开阔。他同时面向学界与大众写作，专注缜密，科普亲切，广受讨论。在《皇帝的新脑：通向实在之路》中，他追问物理与数学的基础，并尝试连结思维、意识与计算。他先后在英美多所顶尖学府任教与研究，建立广泛的学术合作网络。其研究横跨纯数、应数、物理与哲学评论，形成少见的跨域视野。也正因如此，他更愿直面宇宙如何展开大爆炸之前是什么这类底层问题。其中最具代表性的主张之一便是循环宇宙论，此即共形循环宇宙学 CCC。 大爆炸是两个漫长纪元之间的过渡，而非绝对初始。于他的景象里，当前纪元的遥远未来，物质稀薄，黑洞蒸发，可经数学缩放而对接成下一纪元的新大爆炸。其关键工具为共形变换，保角不保尺，将庞大且严重膨胀的宇宙应到下一轮炙热紧凑的早期状态。Eon 纪元一词被用来指称这样一个极其漫长的宇宙阶段，因此可观测宇宙不过是无数纪元中的一段插曲，前后或仍有漫长序章与尾声。历经多年酝酿，他在演讲与时间的循环中系统阐述这一构想，其核心目标之一是化解早期宇宙低熵的难题，并提供超越单一开端的一致途径。循环模型绝非标准宇宙学的微调，而是观念坐标系的更换。你得把极早与极晚视作可对接的两端，重新审视它们的映射关系。他 他特别指出，在极端未来，一些物理量失去固有尺度，标尺可被任意伸缩。当宇宙止于无质量粒子与场时，透过共性压缩长度与时间，遥远寒冷的未来便可与下一轮炙热开端相匹配。而黑洞的蒸发、资讯散布与落入物质的命运，对于让此转换符合热力学账本至关重要。
Our galaxy has a black hole which is about 4 million times the mass of the Sun. There are lots of smaller ones undoubtedly going around, but the one at the middle is extremely big. Now, what happens to the black holes eventually? Well, as you see, they evaporate away by Hawking evaporation. And then when they've all gone, how long does that take? Well, for the really big ones, you have to think of something like a googol years. What's a googol? Well, that's 1 followed by 100 zeros. And that's the sort of time you're going to have to wait before all the black holes have gone. The really big ones take the longest to go away, and the smaller ones go away much more quickly. But after they've all gone, now I thought it was pretty boring before, sitting around watching for a black hole to evaporate away. Now that's dead boring. When they're all gone, that's very boring. But then I began to think, who's going to be bored by this? Well, photons probably, mainly photons. And it's really hard to bore a photon. It's hard probably for 2 reasons. One is it probably doesn't experience anything. But the other is from relativity effects, photons don't experience time at all. The time from creation of that photon or whatever happens to it is nothing to that photon. So that it gets right out to infinity, and it's as though this just happened instant.
于是广义相对论的几何语言与熵增时间之间的统计叙事得以在同一画布上对话。为了寻找可验证线索，彭罗斯与合作者古尔扎迪安提出一项观测特征作为检验。他们检视宇宙微波背景、早期宇宙的余晖，指称在温度起伏图中出现方差偏低的同心圆环。解读是，那或是上个纪元的剧烈事件，如超大质量黑洞碰撞，跨纪元传递后在 CMB 中留下的波纹印记。此说一出即备受瞩目，因为它为超越标准大爆炸图景的理论提供了具体观测线索。同时，这项主张也引来多个团队的审慎重验与方法检核。数个独立小组审视资料与演算法后认为，该特征与标准宇宙模型下的统计预期并无显著偏离。换言之，初始分析未充分校正统计效应，在严格处理后，同心环并不显著异常。此类往返在科学界极常见。新发现再检验再修正，形成健康循环。有趣主张会驱动群体去比对方法，寻找更干净与精确的数据集，进而提升整体研究品质。重分析后的共识是，圆环证据薄弱，但不等于整个循环途径无效，顶多说尚未被观测支持，也就是说尚无定论。要改变共识，仍仰赖未来更高灵敏度的观测与严密分析。撇开宇宙学本身，他也经常提醒大家，现行理论有其边界，切勿过度延伸诠释。他特别质疑部分膨胀模型对初始条件的精细调写，以及相关概率解释是否站得住脚。彭罗斯并非全盘否定，他是呼吁对替代路径保持开放心态，以数据而非流行来决定取舍。他的批评着重方程自洽与可检验性，语气理性克制，诉诸技术细节而非立场对立。他点出一系列技术性难题，几率评估如何界定，初始条件如何设定，以及理论预测与实际观测该用什么统计准则来一一比对。这种立场既赢得敬重，也引来质疑，但恰好体现他的角色，宁愿严肃面对概念根基，也不因潮流而轻易点头的数学家。要把握彭罗斯的起源观，首先得把两个相近却不同的问题分清，避免混为一谈而误解重点。其一，是什么物理机制导致早期那团高温高密的宇宙原汤，也就是我们口中的大爆炸状态？其二，则更形上，为何会有这些定律？为何自然常数取这些数值？这属于哲学层面的追问。彭罗斯的科学主张重点聚焦在前者，也就是对可检验的物理机制提出途径。他构筑的图像是我们所现的早期宇宙，其实是更古老一个纪元经共形转换后的延续。在技术层面， 他从不诉诸超自然或神奇，而是坚守数学与物理的语言。相反的，他寻找的是能跨越唯一开端且与现有定律相容的数学描述。这并非声称解除为何存在的终极答案，而是试图把起源带回可计算与可检证的科学边界内。他的论证以几何学为骨架，结合热力学与天体物理机制，形成一套互相支撑的框架。几何面向来自共性变换，它改动尺度与时间度量，却保留角度结构，使两端时代得以对接。之所以引入热力学，是因所有宇宙学都必须交代时间之箭何以指向未来，熵为何单向增加。彭罗斯长期追问，为何早期宇宙的熵远低于直觉？这正是他循环图景想破解的症结。他的循环图景让低熵开端嵌进更长历史，熵在每个纪元上升，而边界经共性映射产生可对接的重置。在天体物理上，他特别强调黑洞与其最终蒸发的关键作用，牵动整体熵涨。黑洞如何蒸发，质量与资讯在膨胀中怎样弥散，将决定共形拼接在物理上是否可行。多层次交缠式图像相当复杂，必须汇聚广义相对论、量子场论与统计物理的合力。不过，批评者也陆续提出数项反对意见，要求更扎实的推导与证据。有人认为共形匹配虽优雅，却缺少源于量子引力的完整机制，而那才是最微尺度时空的终极描述。也有人指出，目前援引的观测线索经统计重审后说服力有限，尚不足以定论。另有疑虑在于熵的核算与黑洞物理的细节，所需条件是否真能在宇宙演化中达成。简言之，这是一套很有启发的构想，但仍有待解的关键环节，未卜其前，难以替代既有主流。彭罗斯也坦诚上有缺口，将其视为正在推进的研究蓝图，而非已完工的最终说明。把它放回更大脉络时，我们需同时比较其他主流路线，才能看见差异与互补。例如，标准膨胀模型以短暂指数膨胀期，成功解释几何近乎平坦与 CMB 统计等多项观测特征。也有人走量子宇宙学路线，盼把量子与引力统合，避免在最初时刻出现奇点。另一些则援引多元宇宙，主张不同区域可能拥有各异常数与自成历史。彭罗斯的共形循环宇宙学便是众多候选之一，提供不同的切入角度。它的着力点不同，强调纪元对接与几何映射，而非新增场或口袋宇宙。换句话说，它不扩充内容，而是用共形几何重新塑形关系。各种路径皆有优缺，学界以自洽性与可否解释、预测观测为评判尺。此外，彭罗斯也关注物理与心智的连结，将视野延伸至认知层面。在多部著作中，他主张仅以传统计算模型难以穷尽一时，量子效应或许在认知中扮演角色。他与哈梅罗夫提出有序客观还原 Orchestra OR， 认为微观结构内的特殊量子坍缩可能把量子力学同意识现象接起来。这一路线争议不断，从生物可行性到物理细节接受检视。不少神经科学家与物理学家质疑其生物条件与实证支撑，连量子坍缩本身亦有多种竞品理论。尽管如此，这些提案展示了他议题跨度之大，敢于跨界抛出新问题。他把焦点从时空几何延伸到心灵和以为心灵背后或涉哪些物理过程。这些研究未必直接牵动宇宙模型，却折射他一贯的风格，用数学触碰人类最根本的经验问题。每当新观点意图解释宇宙深层特征，学界往往循序经历若干阶段的回应。若它能解决明确痛点或提出可测预言，最初便会引发高度兴趣与期待。接着各组会重算、复现并寻求独立数据验证，确认其稳健性。若仰赖新观测，则需经不同仪器与方法反复检验，排除系统性误差。若属概念或数学建构，则着重逻辑链条与隐含假设的逐项盘点。就彭罗斯的循环观而言，这套流程已公开上演，众说并陈。CMB 中的圆环讯号先悉经再被细审，争点聚焦于它是实际还是统计假象。此过程并非他所独有，几乎所有重大新说都必经此关。科学正是如此，在时间中自我校准，逐步修正并打磨理论。也有观众更想质问， 究竟是什么创造了宇宙，而非仅讨论纪元对接的机制。简单说，彭罗斯的科学路线不引入超自然造物者，始终以物理叙事为本。他提供的是数学物理框架，把一个纪元的遥远未来应到下一纪元的起点，扩充单一热开端之外的解读。他从黑洞行为、质量资讯流、共形几何及量子引力可能性中寻找让延续可行的机制，这与终极形上回答不同。他也承认仍留多处空白，尤需更成熟的量子引力与更清晰的观测指标。对寻求自然化解释的人而言，这是一种把问题落回经验与数学可探路径的尝试，而非诉诸权威或传统。回望历史脉络，有助理解他主张的分量与其引发讨论的原因。至20世纪中叶，相对论与观测天文结盟，让宇宙学真正成为一门经验科学。起点定理揭示，经典物理若硬性外推，会直达理论自我失效的边界。这逼使研究者要么寻新物理以抹平起点，要么另辟叙事来理解它。彭罗斯先论起点，再推循环，揭示回应爱因斯坦方程的数学后果与膨胀 CMB 的观测事实。他的套路是由方程与既知数据出发，评估能否做出自洽延伸，不予局部偷步。此法特别适合难以直测的议题，因其牵涉极端尺度与漫长时间。未来待解的是，共形循环是否能跻身主流，或终究停留在耐人寻味的备选。关键在两端，一是补其与量子引力对接的理论地基，二是找到可清楚区别的观测证据。随着 CMB 与引力波量测日益精准，未来数据或可对竞争途径做出裁决。在尘埃落定前，它仍是一个严肃且数学上站得住脚的提案，迫使我们审视主流假设的根部。彭罗斯的一生证明，用数学照亮宏大问题能带来持久而深远的价值。他既提出限制理论边界的定理，也尝试把既有理论扩展到更宽的解释版图。至于其宇宙图景能否写实漫长史诗，仍待时间与数据裁定，但其影响已然深植学界。他推动研究者更精确陈述假设，优化统计处理，并以全新术语讨论极早极晚宇宙的联系。这些改进皆属实打实的成果，直接提升研究品质与可验证性。科学史一再示范，即便某提案最终未过严审，也能藉校正问题与方法而推动整体前进。彭罗斯的构想已促成这种良性循环，未来几年势必还会激发更多研究与辩论。若它的图景正确，我们眼前的宇宙不过是无尽乐章中的一个节拍，前后仍有长长的旋律。感谢收看，别忘了订阅与分享。下一集我们将继续用通俗又严谨的视角，带您更深入走进宇宙秘境。